So let's look at some examples now, a couple examples, and work through them and see how we can use this in practice. Okay, so I look at this. I've got an expression here, 5x squared plus 20x plus 6 over a cubic. And first I want to check, is this improper? No, the denominator has a cube, and the numerator's of degree 2, so we're not improper. We can just continue and start with the process of partial fraction decomposition. So I want to factor that denominator, right? And so just let's do that. X cubed plus 2x squared plus x is, well, I see I can pull out an x, and that leaves you with x squared plus 2x plus 1, and I recognize that as a square, so that's x times x plus 1 squared. So what I have are two linear factors, one of which has multiplicity 2, okay? And my expression then, is going to be 5x squared plus 20x plus 6 over x times x plus 1 squared, and that breaks down into an a over x plus, we'll just say a b over x plus 1. Because this has multiplicity 2, we also have a c over the quantity x plus 1 squared. Okay. Now my advice to you at this point is to clear the fractions, right? We're going to multiply by the denominator, right? X times x plus 1 squared, or x cubed plus 2x squared plus x if you prefer, right? But we're going to multiply both sides by the denominator, and we're going to get from that the original numerator, 5x squared plus 20x plus 6, equals, and now I'll just cancel the terms, or excuse me, cancel the factors that appear in the denominator of each individual term here. So the x is going to cancel here, and so this is going to be a times x plus 1 quantity squared plus b times x times x plus 1 plus c times x. Okay, and really this equality, really is these are identically equal, right? So we're looking for a, b, and c's that make this identically equal, not just equal for some x, right? And I should have mentioned that earlier, right? This expression, our original expression, is the same as the expression on the right for all x's, and so we have an identically equal situation here, not simply an equality that we're solving, right? And that is important because it allows us to very easily solve for some of these things, right? So for instance, by choosing x wisely, we can eliminate one or more of the a, b's, and c's and solve for the remaining one. So for instance here, right, I can choose, because bx and cx both show up here, if I choose x to be 0, those terms will drop out, and 0 plus 1 is 1, and 1 squared is 1, so I'm going to get a on this side, right? And if I plug in zeros on this side, I get 6, right? So if I let x equal 0, then I get that a is 6. Great. Now I can sort of plug that in and keep going, right? Likewise, if I let x equal, I look at the factors here, -1, right? X plus 1. If I let x equal -1, then a and b drop out, and that gives me a negative c, right? So let's look at that. So that's negative c, and on this side, we're going to get -1 squared is 1, so that's 5. 5 minus 20 is negative 15. Negative 15 plus 6 is negative 9. So negative c is negative 9. That means c equals 9, right? And now I can solve for b as well. Let's plug the a and c in just so that we have that to work with. This is going to be 6 times x plus 1 squared plus I still don't know b yet, bx times x plus 1 plus 9x. Okay, solving for b, I can either multiply all this out and then find the b that causes the coefficients to match, or I can just pick another value for x at this point and solve and see which one, what b makes that work. So, like for instance, let's just let x equal 2. Okay. Well, on the left-hand side, I'm going to get 2 squared is 4. I get 20. 20 plus 40 is 60, so I'm going to get 66 on this side. And on this side, I'm going to get 2 plus 1 is 3. 3 squared is 9. 9 times 6 is 54. Plus 2 times, 2 plus 1 is 3 times 2 is 6. So this is 6b plus 18. And then I can just solve this for b. What do we get here? We get 6b equals, what's that, 64, 72, subtract 72, we get negative 6, and that gives us that b equals negative 1, right? So I've now written this here as, what do we say, 6 over x plus negative 1 over x plus 1 plus 9 over x plus 1 squared, right? And we can now integrate this expression instead of the original expression. So let's go ahead and do that on the next page here. So let's remember 6, negative 1, and 9. So we rewrite the integral as the integral of 6 over x plus negative 1 over x plus 1 plus 9 over the quantity x plus 1 squared. And we can integrate each term individually to get the answer, right? So this becomes a pretty easy integral. We're going to get 6 times the natural log of x minus the natural log of x plus 1. And then, 9 over the quantity x plus 1 squared, we can sort of do a mental u substitution of u equals x plus 1, and then we've got 9 times 1 over u squared, or u to the negative 2. So that's going to be minus 9 over x plus 1 to the first, or 9 times x plus 1 to the negative first, if you will, as our integral there, and then plus c. And we're done. Let's look at one last example here. This one we've got a quadratic factor and then 2 linear factors as well that we didn't quite factor out yet. And let's work through that and see how that works and get a result. So writing out the original numerator, we have this. The denominator is going to be x times x minus 1 times x squared plus 4. And of course that quadratic factor here doesn't factor, so we're going to have to leave that as a quadratic and recognize that this will decompose into an a over x, a b over x minus 1, and a cx plus d over x squared plus 4. Multiplying by the original denominator on both sides, we clear the fractions, and we get a times x minus 1 times x squared plus 4 plus b times x squared plus 4 plus cx plus d times x minus 1. And again, thinking about beneficial values of x to plug in, we can eliminate some things. So if we let x equal 0, then that eliminates both the b and the cx plus d's, because we get zeros in for these x's. And so we get from that on the left-hand side, 0 minus 8, we get negative 8 is equal to a times negative 1. 0 minus 1 is negative 1. 0 plus 4 is 4. So this is a times negative 4, okay, which implies that a equals 2. Likewise, we can try to eliminate a and cx plus d by letting x be 1. So if x equals 1, then we get on the left-hand side, 2 times 1 is 2. 2 minus 4 is negative 2. Negative 2 minus 8 is negative 10. And on the right-hand side, a goes away, cx plus d goes away, and we're left with 1 here. 1 plus 4 is 5. So this is 5b, and that implies that b is negative 2. And so now we've got two of the values. We need to find the other two. And we could continue by we can't continue by picking another value for x in this case, because in order to eliminate a and b, we've got this quadratic, and we can't make the quadratic equal to 0 without using imaginary numbers. So another strategy would be to simply look at the coefficients here and make things match up. What I mean by that is we know that a and b are 2 and negative 2 respectively, and we know that the coefficient of x cubed has to be 2. So let's look at the first two terms and see what has to be the case for c. So we see that we can get an x cubed out of the a term by doing x squared here. And so that's going to give us 2x cubed, right? So just sort of write that. 2x cubed from the a term. I'm going to undo that. Let's just write that over here. So for the x cubed term, I'm getting, from the a portion, I'm getting a 2, right? Because a is 2. 2x cubed. From the b portion, I can also get x cubed, x times x squared, and b is negative 2. So that's plus a negative 2. So a and b together, these two terms are producing 0x cubed, right? But I want 2x cubed, and so that has to be given entirely now by the c. Well, I can get cx cubed by cx times x times x. I can't get dx cubed because d can only multiply x and another x, so I can only get a maximum of x squared with the coefficient of d. So that means that negative 2 plus negative 2 plus c together have to equal 2, and that means that c itself is 2. So now I've got a, b, and c. All I need left is d. So to find that d value, I have a couple choices. I could do something similar to what we did to find the c value. For instance, the d, I could look at the x squared term, for instance, right? I can get dx squared by doing d times x times x. Or I could just look at the x term, right? D times x times negative 1, and see what, and realize that those have to add up to negative 4 x's, right? And so I could look at a times negative 1 times 4, and bx wouldn't, bx times 4, right? Or the other thing I can do is recall that, again, this is an equivalence. These are identically equal, not just equal. And so I could choose a value for x and solve for d now that I know a, b, and c. So let's just do that in this case. Let's say, for instance, x equals 2, and see what we produce. So on the left-hand side, 2 cubed is 8. 2 times 8 is 16. 16 minus 8 is 8, and 8 minus 8 is 0. right? So 0 on the left-hand side is equal to, well, I know a is 2, so x is 2. 2 minus 1 is 1. Okay, 2 squared is 4. 4 plus 4 is 8. 8 times 2 is 16. So that's the a portion, because a is 2, plus b is negative 2. So I'm going to get negative 2 times 2 is negative 4. 2 squared is 4. 4 plus 4 is 8. I lost what I said. What was that? 2 times negative 2 is 4. 8, so that should be negative 32, if I did that right. Plus c is 2. So 2 times 2 is 4. Since this is with the d, we'll say 4 plus d times 2, and 2 minus 1 is 2, so this is times 2, and that equals 0. So what do we get? Negative 16 here, plus 8 plus 2d, and so negative 8, so 2d equals 8, and that means that d equals 4. Now let's wrap it up by performing the integration. Rewriting the original integral as the partial fraction decomposition. So the integral that we get now, having broken it down, is the integral of 2 over x, a over x if you will, plus negative 2 over x minus 1, plus 2x plus 4 over x squared plus 4 dx. And some of this is easy and some of this isn't. So 2 over x, okay, I see that that's 2 times the natural log of x. Likewise, this is going to be minus 2 times the natural log of x minus 1, absolute value. But now we look at this, and it's not immediately obvious how to integrate this. I see, if I have a u as x squared plus 4, that the du would be 2x, and that's good if I could split that. So maybe we should split this into 2 fractions. So we'll write this as the integral of 2 over x plus negative 2 over x minus 1 plus 2x over x squared plus 4 plus 4 over x squared plus 4 dx. And now, so this third term is a simple u substitution, and so we're going to get the natural log of x squared plus 4, right? Because if we work the derivative of that, it's going to be 1 over this times the derivative of our x squared plus 4, which is 2x. Great. And then this last one, you may or may not remember, is the arctangent. This looks like an arctan derivative, so if we want to integrate that, this is an arctan form. So our arctangent derivative, if you remember, or arctangent integral, if you have something like a u prime over a u squared plus a squared, then what we get out of that is a 1 over a arctan of u over a. Okay, now in this case our a is 2 and our u is just x, so we're going to get 4 times 1 over 2. Okay, so a is 2, so 4 times 1 over 2, which is 2, times the arctangent of our u, which is just x, over a, and then plus c. So yeah, we do kind of want to refamiliarize ourselves with some of those inverse trig integrals and derivatives to make sure we can perform that. So there you go. There's another example of a partial fraction decomposition and integration.